Okay, so just to review where we left off talking about titration. And titration is when you mix an acid and a base and you produce a salt and water. And we use the titration process when we know the concentration and volume of either the acid or the base, and then we use a certain volume of the other to neutralize the solution so that we can figure out the concentration. And this is often done using an indicator, such as phenolphthalein. So we'll add a couple of drops of phenolphthalein indicator to the acid. It's clear in an acidic solution. And then we add base very slowly, drop by drop, until the solution turns a very light, dusty pink. Anyway, let me review example problem 1 and sample 2 so you can see the difference. In sample 1, our H to OH ratio is 1 to 1. We have 1 H in the HCl and 1 OH in the NaOH, and that's going to make water. So we can simply just substitute the values into the equation. We have the volume of the acid, we know the molarity of the base and the volume of the base, and we can solve for the molarity of the acid. In sample problem 3, our H to OH ratio is not 1 to 1. We have 2 H's in H2SO4, and we have 3 OH's in the AlOH3. Now there's 2 ways that you can do this problem, and it's completely up to you, whatever is easier for you to remember. In the example that they use in the textbook, they take the molarity of the acid and they multiply it by 2 because there are 2 H's, which you can see right there. Then they take the molarity of the base and they multiply it by 3 because there's 3 OH's. They then use those molarities in the actual formula. Now, what I do is I just usually substitute in the formula. I usually just do MaVa equals MbVb. And what I build into my formula is the number of H's and the number of OH's. So how I would set the formula up would be I would have 2 H's times the molarity of the acid, which is 3, times my volume, I don't know that, equals the molarity of my base, which is 1.2, times the volume of my base, which is 50, times 3 for my OH's, and solve that way. Whatever easier for you, but you have to realize that when your H to OH ratio is not 1 to 1, that you need to do something slightly different. So I believe we did this one problem on the left in class. If you weren't here, I would suggest that you pause the video and do it, and then also do the one on the right, and then check your work. So on the problem on the left, we're going to use the formula MaVa equals MbVb, and we simply substitute in. The molarity of our acid is 6. We don't know the volume. We know the molarity of the base is 2, and the volume of the base is 39. So solving for Va, we get 13 milliliters. So on the right, how much 3 molar NaOH is needed to neutralize 30 mils of 0.75 molar H2SO4. Well, the first thing I notice is that my H to OH ratio is not 1 to 1, and I like to use my formula, but you could have certainly done it the other way. So I have 2 H's in the H2SO4, my molarity is 0.75, and my volume is 30. And then I know my molarity of my base, which is 3. I don't know my volume, but I have 1 OH. So solving for the volume of base, I get 15 milliliters. Moving on, we're now going to talk about a buffer. A buffer is defined as a solution that resists a change in pH when limited amounts of acid or base are added to it. A buffer is also known as a shock absorber, and we usually just call it a buffer, not a pH buffer. The most common buffers consist of approximately equal molar amounts of a weak acid and a salt of a weak acid. So that's approximately equal molar amounts of a weak acid and a salt of its conjugate base. For example, if we dissolve 1 mole of acetic acid and 1 mole of its conjugate base in the form of sodium acetate in water, we have an acetate buffer. So let me explain that. Acetic acid is HC2H3O2. If I were to separate this into its ions, I get H plus and the acetate ion. A salt, right, its conjugate base, which refers to this, in the form of sodium acetate. So NaC2H3O2. So this is your acetic acid, and this is the sodium acetate. So if I have 1 mole of both of these, this is my buffer pair. I do want to point out that acetic acid is also written as CH3COOH. That is synonymous with HC2H3O2. So they both have, here's your 2 C's, your 4 H's, and your 2 O's. Just 2 ways to write it. The first way, the CH3COOH, is writing it as an organic acid in the organic form, and the HC2H3O2 is writing it in the way that we write all acids in the IUPAC system. So on the next page, you're going to see that they write it this way, and I want you to realize they're talking about the same thing. So here is acetic acid, and when it's in water, remember it's a weak acid, very little of it is going to dissociate. Into the acetate ion and hydronium. If I add a strong acid, though, such as HCl, the added H3O ions from the HCl react with the acetate ions and are removed from solution. If we add a strong base, such as NaOH, the hydroxide ions, or OH minus ions, react with the acetic acid right here and are removed from solution to form the acetate ion and water. So in one instance, you've got the acid reacting with the small amount of acetate ion that dissociated, and it's creating the acid and water. And then if I add a base, the acid that was formed is going to react with the base to form the acetate ion and water. So you have this up and down homeostatic movement going on, and that's why pH buffers resist pH change. Here's another way to look at it. If I have, for example, a phosphate buffer that's prepared by dissolving 0.1 moles of sodium dihydrogen phosphate, which is a weak acid, and 0.1 moles disodium hydrogen phosphate, the salt of its conjugate base, in enough water to make 1 liter solution. If I had that, and then I add either 0.01 moles of acid or 0.01 moles of base, you can see that the pH changes only by 0.09 units. So let's say that my pH of the buffer system is 7.21. If I add 0.01 moles of HCl, my pH is now going to be 7.12. You can see that it decreases by 0.09. And if I add 0.01 moles of NaOH, it's going to go to 7.30. So very little change in pH when we add an acid or a base. One thing that we need to remember about buffers is how can we figure out how to make them. And what you have to remember is the pH of the solution. This is really important. The pH of the solution will be equal to the pKa of the weak acid. Be equal to the pKa of the weak acid. So how do we find that? So pH of the buffer solution is equal to the pKa of the weak acid. And the pKa is equal to the negative log of the Ka of the weak acid. So for example, if we want a buffer with a pH of 9.14, then we can mix equal molar amounts of boric acid, which has a pKa of 9.14, and its conjugate base, sodium dihydrogen borate. These are just examples. So you have to find a pKa, and that matches up to the pH that you want. And sometimes you don't have a pKa list, so you have to take the negative log of the Ka. Another vocab term that is important is buffer capacity. This is the amount of hydronium or hydroxide ions that a buffer can absorb without a significant change in pH. So this is the amount of acid or base that you can add to a buffer system before it reaches its floor and or ceiling. After that, you're going to have a drastic pH change. So the buffer capacity depends on two things, its pH and its concentration. So for pH, the closer the pH of the buffer is to the pKa of the weak acid, the more symmetric the buffer capacity is, meaning the more you can add without it resisting, so that it resists the pH change. The further your pH is of the buffer system from the pKa, the less you'd be able to add. And then concentration. The stronger your acid or base, the greater its buffering capacity. The average pH of human blood is close to 7.4. So any change greater than 0.1 pH unit in either direction can cause illness. So if the pH goes below 6.8 or above 7.8, this could result in death. So there are 3 buffer systems that the body uses to regulate pH, blood pH. The most important is the carbonate buffer system. And this is comprised of the weak acid, carbonic acid, and its base, hydrogen carbonate. Now, the pKa of this system, the buffer system, is 6.37. And because the pH of an equal mixture of the weak acid, carbonic acid, and its conjugate base, the hydrogen carbonate ion, the pKa equals the pH. And I told you that on a previous slide. So the pH then equals 6.37. So as I said, the human blood is close to 7.4. Well, the only way it can remain close to 7.4 is if the concentration of the carbonic acid and the conjugate base, hydrogen carbonate, are not even. The actual ratio is 10 to 1. Or 1 to 10. So 1 to 10 for the acid to the base. And the reason why this makes sense is because this system prefers to buffer acids. If I add additional acid, the acid will be neutralized by the conjugate base, the HCO3 minus ion, which is present in the higher ratio. This will then raise the ratio and decrease the buffer capacity because the conjugate base is neutralizing the acid. And this actually makes sense because in normal conditions, there's larger amounts of acidic substances entering the blood than there are basic substances. The second most important buffering system is the phosphate buffer system, which is made up of dihydrogen phosphate ion, which is the H2PO4, and the hydrogen phosphate ion, which is the HPO4 2-. And in this case, the ratio is 1.6 to 1, in which case the HPO4 2-, so this is 1 to 1.6. So here's your H2PO4- and HPO4 2-. Now this still works better for acidic solutions. However, this system has a pKa of 7.21, which you know is equal to the pH. So this is closer to the actual pH of the blood. So the last important equation in this unit is the Henderson-Hasselbalch equation. And this equation is used to understand the relationship between pH and the pKa. And then it also includes the concentrations of the weak acid and the conjugate base. Now, here is the actual equation that you use, but I rewrite it, and instead of A- over HA, it's easier for kids to remember that it's the concentration of the base over the concentration of the acid. So pH equals the pKa plus the log of the concentration of the base over the concentration of the acid. The only thing you need to remember is if you are not given the concentration, then you need to use the molarity formula. Molarity equals moles over liters first in order to get the concentrations. In this example, it says, what is the pH of a phosphate buffer solution containing 1 mole of NaH2PO4, so sodium dihydrogen phosphate, and 0.5 moles of disodium hydrogen phosphate dissolved in enough water to make 1 liter. So here you can see that they gave you moles, not concentrations, but they did give you the liters. So if we were actually to calculate the concentration, molarity equals moles over liters. So 1 divided by 1 is 1. So the concentration of the dihydrogen phosphate ion is 1 molar, or 1 mole per liter. And the 0.5 divided by 1 is 0.5 moles per liter. So putting this into our formula, pH equals the pKa. So we would need to look up the pKa in our table. So in table 8.3, the dihydrogen phosphate ion has a pKa of 7.21 plus the log. So you're going to take 0.5 divided by 1, which is going to be 0.5. Take the log of that on your calculator and then add 7.21 to it, and you come out with 6.91. And that's because when you take the log of 0.5, you get a negative number. So this is 7.21 plus a negative number, which gives you 6.91. All right, let's try one of these. What is the final pH of a solution made by mixing 100 mils of 0.5 molar acetic acid and 100 mils of 0.1 molar sodium acetate? Assume the pKa for acetic acid is 4.76. So in this problem, they gave you milliliters, which is not necessary. It's supposed to throw you off because you already have the molarity. So remember, the pH is equal to the pKa plus the log of the concentration of the base and over the concentration of the acid. So in this case, pH equals 4.76 plus the log of the base, which is 0.1 over 0.05. And when I do the math on this, I wind up getting a pH equal to 5.06. All right, try the next one. So you have to look up the pKa of lactic acid in table 8.3 in your text. You'll be given that for the text. And it's 3.86 plus the log of the base, which is the 0.4, over the acid, 0.8. And when you do that, you should get a pH equal to 3.56. So we're going to end with a little bit of history. The original laboratory buffers for use in biochemical studies were made from simple acids and bases, some household items such as acetic acid, which is vinegar, phosphoric acid, citric acid, which is your vitamin C, and their conjugate bases. However, they found over time many of them had limitations, such as their pH changed too much, if the solution was diluted, or if the temperature was changed. And they could also permeate cells in the solution and then it changes the chemistry in the interior of the cells. So, Any Good, who is a scientist, developed a series of buffers that consist of something called Zwitter ions, which are molecules that do not readily permeate cell membranes. So the Zwitter ions, or Zwitter ion buffers, as they're commonly called, work better because they're resistant to concentration and temperature changes. The most common synthetic buffers used today have very complicated formulas. One is called MOPS, MOPS. You don't have to know how to pronounce it, and you don't have to know or understand the structure. The most important considerations are the pKa of the buffer and the concentrations that you want to have. And that's why we use the Henderson-Hasselbalch equation. I want you to take a few minutes and read this page and then go on to the next screen. So what causes respiratory acidosis? Well, two things. One is difficulty in breathing, which can be caused by a number of diseases, such as pneumonia, emphysema, congestive heart failure, or asthma. Or in any situation where you're diminishing the amount of oxygen that reaches the tissues, and you wind up with a buildup of CO2 because it's not leaving the lungs. Another way is by holding your breath. If you hold your breath to the point where you can't hold it anymore, you might experience burning in your muscles, and this is due to the fact that the pH of your blood decreases and that buffer system is disrupted. And the other question is, what causes metabolic acidosis? There's two things: either somebody that's starving or fasting for dietary reasons, and or heavy exercise. So when you're not putting enough calories in your body is going to burn its own fat. And the products of burning your own fat are acidic compounds that are now in the bloodstream. Specifically, exercise, you produce huge amounts of lactic acid. And that's what makes the muscles feel tired and sore. But it lowers the pH of the blood because the lactic acid is now in the bloodstream. And that's also what can then lead to rapid breathing and dizziness. And it's not really, again, because you're trying to get more oxygen, but it's because you're trying to get the CO2 out of your system. Okay, that ends chapter 8. Please remember I changed the order of the assignments. I will put them on Brightspace right now when they are due, but there was some conflicts in the syllabus. So please, if you weren't in class on Thursday or you weren't on time on Thursday, please make sure you check out Brightspace to get those changes. All right, enjoy your break.